You know, it's actually kind of wild how we just completely surrender to a phrase without ever really thinking about what it actually means.
Oh, absolutely. We just accept the label and move on.
Right. Like, think about the dawn of aviation. When humanity finally built a machine that could actually fly, we didn't all stand around Kitty Hawk, look at the right flyer, and call it, artificial flying.
Nobody was saying, look at this fake bird.
Exactly. We just called it flying because, yes, the struts were manufactured, the engine was built in a shop, the vessel was totally synthetic.
Right, but the aerodynamics were real.
Yes. The lift, the physical displacement of the air to get off the ground, that was an actual naturally occurring process. We just used a man-made machine to execute it.
Which is a perfect analogy. The phenomenon itself isn't counterfeited just because the substrate doing the executing is non-biological.
Right.
Flight is just governed by fluid dynamics and physics. A bird uses feathers and hollow bones, and a 747 uses aluminum and jet fuel.
Yeah, but still flying.
Exactly. The action taking place is a real, measurable interaction with gravity. We don't categorize a Boeing flight as a simulation or some parlor trick just because it didn't hatch from an egg.
But then we cross the threshold into computer science, and suddenly this one phrase totally dominates everything. Our headlines, our economy, our whole technological paradigm.
Artificial intelligence.
Artificial intelligence. And I keep wondering, what if that phrase, this foundational label we slapped onto the most important tech of our era, is actually misleading?
It's more than misleading. It might be a fundamental cognitive blinder.
Right. Because what if our absolute obsession with the word artificial is preventing us from understanding the actual mechanics of what we're building? And more importantly, where these massive systems are destined to just hit a thermodynamic wall?
That is the exact philosophical pivot we need to make today. Because, the word artificial carries this inescapable connotation of simulation.
Like it's an illusion.
Right. It implies something that looks like the original, but is fundamentally hollow. And if you operate under the assumption that we are merely simulating intelligence, you categorically misunderstand the engineering reality of a neural network.
We start judging it like a magic trick instead of a machine.
Exactly. We stop evaluating the system based on the physical laws of computation, and we start evaluating it based on theatricality.
Yeah.
How human does it sound?
Which is exactly the trap we are dismantling today in this deep dive. We are looking at the highly provocative work of Guy Lakeman, specifically his treatise, The Biological Architecture of Machine Intelligence.
It's a fascinating piece of work.
It really is, and we're zeroing in on a section that basically rewrites this whole premise. His argument is that intelligence is not artificial. Intelligence is a process.
Which totally shifts the paradigm.
Yeah, we are going to basically rip the casing off the current digital models that everyone is so obsessed with right now, the massive large language models, and expose the severe structural and, frankly, energy limitations hard-coded into them.
And then we'll look at Lakeman's proposed blueprint for evolving these statically bound systems into what he calls a superintelligence know-all.
The mission here for you listening right now is to move past the surface level awe of chatbots. We need to look intimately at the actual mechanics of computation.
Because once you understand how fundamentally inefficient a digital binary system is at replicating neuroplasticity, you see the problem.
Yeah, the current trajectory of just throwing more compute and more power at these models is basically a brute force approach. And it has a very hard, very fast approaching ceiling.
It really does.
So whether you work in tech or you're looking at the silicon supply chain or you're just trying to keep up with the endless AI hype, understanding this difference between biological and digital architecture is the master key.
It's the only way to know what's real breakthrough and what's just throwing more GPUs at a broken paradigm.
So let's jump straight into Lakeman's foundational axiom. He states that intelligence is a well-defined process with measurable metrics. It's not magic.
No, it's not some ghost in the machine. It's a definable, quantifiable process. And to establish that, Lakeman demands a rigorous redefinition of our vocabulary.
He really goes after the word artificial.
He does. He argues that artificial is only accurate when it describes the replication of an item. He uses medical examples, right? Like a prosthetic hip or an artificial heart valve.
Okay, so the item is artificial.
Yes. The item itself is artificial because it was manufactured out of titanium or synthetic polymers to replace a biological original. The physical object is the fake.
But the utility of that object, the process, is completely real. Like if I get an artificial hip, I don't engage in artificial walking when I leave the hospital.
No, you're just walking.
Right. The biomechanical process of moving my mass across the room is real. Or if you engineer a mechanical pump, the titanium parts are man-made, but the displacement of the fluid...
That's not artificial water being moved.
Exactly. It's real fluid dynamics. So the leap Lakeman asks us to make is this. Is calling our current tech artificial intelligence just as absurd as calling a prosthetic leg artificial walking?
It is the exact same categorical error. I mean, if intelligence is defined functionally as the ability to ingest data, recognize patterns, synthesize variables, produce an output, then that process can happen in a machine without the process being fake.
So what did we actually build then?
In machine learning, what we've manufactured is an artificial item. Specifically, we built a digital approximation of the human neuron.
The node in the network is the prosthetic.
Precisely. We built a silicon prosthetic neuron. And because the substrate is silicon instead of biological tissue, we just collectively assume the output must be prosthetic intelligence.
But if the metrics are met, the intelligence is real.
Right. The digital algorithm is the artificial item.
Yeah.
But the execution of logic is a real physical process happening in the physical world.
Okay, but I have to push back on this a little bit, because it feels like this sidesteps the whole functionalism debate.
How so?
Well, if we just define intelligence as input, synthesis, output, are we casting the net way too wide? Like, by that logic, a pocket calculator from 1985 is executing real intelligence.
Ah, I see where you're going.
Right. A calculator takes input, synthesizes it against arithmetic rules, and spits out a true output. But nobody thinks a calculator is intelligent.
No, of course not.
The defining trait of biological intelligence isn't just processing data, it's the way it structurally adapts to novel data. Isn't that why we still use the word artificial? Because the machine's internal architecture isn't adapting like living tissue does.
That is a phenomenal distinction. And honestly, you're anticipating the exact structural critique Lakeman levels at modern LLMs.
Oh, really?
Yeah. You are correct that a calculator is executing a real process, but it's a rigid, rule-bound process. It has zero adaptive plasticity.
It's locked in.
Right. And modern LLMs are obviously vastly more complex than a calculator, but as Lakeman points out, they share the exact same fundamental flaw. They are structurally rigid.
So why is Lakeman so hung up on dropping the word artificial then?
Because he's trying to strip away our anthropomorphic biac. We tend to conflate intelligence with consciousness.
Oh, I see.
We assume because the machine doesn't experience the internal feeling of realizing a truth, its intelligence must be fake. Lakeman is saying, divorce the output from consciousness. The synthesis of info is real. But, as you pointed out, how that synthesis is achieved physically is where digital models diverge wildly from biology.
And wildly inefficiently. Which brings us to the metrics. If we accept that we built a digital replica of a neuron, we have to evaluate how good that replica actually is.
And from a thermodynamic perspective, it's pretty terrible.
It really is. We can't just judge the model by how convincingly it chats with us. We have to look under the hood at the physics of the computation. And this is the most sobering part of Lakeman's analysis, the massive energy crisis of the digital brain.
It's a crisis of scale, really.
Yeah.
To appreciate it, you have to look at what's required to replicate human neuron connections using our current hardware.
You mean the GPUs?
Yeah, the NVIDIA H100s, the massive server clusters training these foundation models. The engineering achievement is staggering, but it's masking a profound architectural inefficiency.
We are paying an unbelievable energy tax.
We really are, because we're trying to simulate continuous biological processes using discrete digital bits.
Let's unpack that for the listener, because we have to look at the actual physics of data storage here. Lakeman makes a sharp distinction between a digital bit and a biological analog bit.
Right. When we talk about a digital bit in a tensor core, we aren't just talking about a theoretical 1 or 0.
It's a physical thing.
Yes, it is a physical transistor holding a charge or releasing a charge. It is entirely binary.
And to represent the kind of high-dimensional data and LLM processes, like these massive vectors and embedding spaces, you can't just use one bit.
No, you have to string together an astronomical sequence of these binary states. You bundle discrete bits into bytes and bytes into massive matrices just to represent a single gradient of a single parameter.
So the digital architecture forces hypergranularity.
Exactly. Because a single bit has no spectrum. It's either fully on or fully off. So to capture any nuance, you have to increase the volume of bits exponentially.
But biological information processing doesn't work like that at all.
Not even close. Biology relies on multiple level analog bits. An analog system doesn't represent information as a binary state. It represents it as a continuous range.
Then we're talking about like chemical gradients in the brain.
Yes, chemical gradients, ion concentrations, action potentials. An analog biological synapse doesn't have to string together a 16-bit floating point number to represent the strength of a signal.
Right. It doesn't need a string of ones and zeros.
The signal strength is inherently represented by the physical volume of neurotransmitters crossing the gap. Because it's a continuous spectrum, the biological bit requires vastly fewer physical operations to achieve infinitely more representational fidelity.
The analogy that always helps me wrap my head around this is a giant physical pinball machine.
Oh, I like that.
Imagine this impossibly massive pinball board with billions of rigid, fixed pegs. And every single piece of data the pinball has to physically bounce its way down through this static maze. In a digital binary system, every single time that ball hits a peg, an active electrical charge has to be applied to register the collision. On, off, 1, 0. You are expending energy at every single microscopic point of friction.
Right, because the transistor has to flip.
Exactly. And in an LLM, you are running trillions of pinballs through billions of pegs simultaneously. The sheer kinetic heat generated by all those discrete impacts is staggering.
It's why tech companies are literally trying to recommission nuclear power plants right now just to cool their data centers.
Which is insane. And that thermodynamic cost isn't just theoretical, it's a hard physical limit.
Lakeman actually points to Landauer's principle to quantify this.
Oh, right, the limit for erasing a bit.
Yes, there is a fundamental thermodynamic metric for digital computation. Erasing a single bit of information, which you have to do to clear memory states and write new ones, requires a minimum energy expenditure of exactly 2.9 times 10 to the negative 21st joules.
Which in physics terms is what, like 0.018 electron volts? Now, to the average person, 2.9 times 10 to the negative 21st joules sounds absurdly small. It sounds like a rounding error.
It does. But in the context of an LLM, we aren't doing a few calculations. When an LLM is running back propagation during training or even just generating a paragraph of text, it is overwriting billions of parameters.
Over and over again.
Yes, passing massive matrices through the GPU memory wall continuously. It's flipping and erasing trillions upon trillions of bits per second.
And this brings up the von Neumann bottleneck, doesn't it?
Oh, absolutely. That compounds the crisis entirely,
Right.
because the energy isn't just spent on the logic gates performing the math.
Right.
In modern AI hardware, the vast majority of the energy is wasted simply shuttling these massive bundles of binary data back and forth between the memory modules and the compute cores,
So every time you move that data, you're paying the toll of Landauer's limit.
multiplied by trillions. The digital prosthetic neuron is fundamentally starved for energy just to maintain its basic operational state.
But the biological brain totally sidesteps this.
Yes, through what Lakeman calls biological stasis.
Which means the hardware of the brain doesn't need this constant high-energy state switching just to exist.
Exactly. The DNA and proteins in the cell nucleus are incredibly low maintenance. A biological neuron does not replicate to process information.
The cellular hardware is static.
Right. When you learn a new fact, your brain doesn't have to spin up a new server rack or write a massive new block of code to a hard drive. It uses the existing physical structure.
Because biological neurons aren't replicating to execute cognitive processes, their baseline energy use is strictly bounded.
The human brain operates on roughly 20 watts of power.
20 watts? That's like a dim light bulb.
Yes. And a single NVIDIA H100 GPU draws 700 watts. And it takes tens of thousands of them to run a model that still can't match the associative reasoning of a toddler.
Which really exposes the dead-end nature of this whole trajectory. If biology gets this profound efficiency because its hardware isn't aggressively state-switching.
And our digital systems are basically giant thermodynamic engines burning power just to shuffle ones and zeros.
Aren't we just optimizing a fundamentally flawed paradigm? We're trying to replicate elegant fluid dynamics by building a bigger, hotter, mechanical pinball machine.
We will inevitably hit a threshold where the power required to scale the matrix exceeds our actual capacity to generate electricity.
That scaling wall is what the industry is quietly terrified of.
Oh, they are. The assumption has always been that scaling laws will hold indefinitely. Just make the parameter count bigger, feed it more data, and boom, emergent superintelligence.
But Lakeman's analysis suggests the scaling law will be broken by physics long before we get there.
It will. But, the energy drain is actually just a secondary symptom.
Wait, really? The energy crisis isn't the main problem.
No, the core issue, the reason all that data has to be aggressively shuffled back and forth in the first place, is an architectural limitation. It's how those digital nodes are structurally organized to communicate.
Right. The energy crisis is just the exhaust of a broken engine. The real problem is the blueprint of the engine itself.
Yeah.
Which brings us to the structural core of Lakeman's argument. The static matrix of artificial intelligence versus the agile axon of biological intelligence.
This is where we have to look closely at how information actually routes through a network.
So to understand the rigidity of LLMs, we first have to look at the physical dynamism of the human brain.
Right. Lakeman highlights a specific anatomical feature entirely absent in modern AI. Agile axon terminal outputs.
Agile axons.
Yes. In neurobiology, information transfer isn't just a math function. It's a physical, topological reality.
Let's break down the mechanics of that agility for the listener. In a biological network, the dendrites are the receivers, right? They take in the chemical signals.
Correct. And the axon is the output channel projecting the signal forward.
But what makes the biological axon agile?
It's agile because it actively physically searches.
It moves.
It literally moves. Biological axons are not static copper wires soldered to a motherboard. During development, and crucially during learning, axons have structures called growth cones.
Growth cones.
Yeah, and they actively slither through the extracellular matrix, following chemical gradients, physically hunting for the specific dendrites of other neurons that they need to connect to.
So the topography of the brain is literally self-assembling.
It's constantly rewiring based on the stimuli it encounters.
That's neuroplasticity in the most literal sense.
Exactly. And Lakeman details how this agile connection transfers data in two distinct ways.
Okay, what's the first way?
First, through weights determined in the connection synapses.
Right. So when an axon connects to a dendrite, the synapse between them can be strengthened or weakened?
Yes. If neuron A consistently fires and triggers neuron B, the physical chemical bond strengthens. That's a synaptic weight. It acts as a filter, modulating the priority of the signal.
Which is exactly what we try to simulate in digital neural networks. We assign mathematical weights to the connections between nodes.
We do. But Lakeman points out a second biological mechanism that we don't simulate at all. Biological neurons can also transfer information through direct presynaptic connections without any weighting filter.
Wait, no filter at all?
None. A direct, unweighted presynaptic connection means the data passes through raw, without being modulated by historical biases or math filters.
How does that work in practice?
Lakeman uses the sensory chain to illustrate this. Say, a photoreceptor in your retina detects a photon, or a mechanoreceptor in your skin detects heat.
Okay.
It transmits that raw, unweighted impulse directly to a dendrite. That receiving neuron then immediately retransmits it via an agile axon chain to other specialized regions of the cortex.
So it's a dynamic, self-organizing pipeline.
Yes. It can prioritize raw environmental data instantly without having to run it through billions of pre-calculated weights.
Okay, so biological intelligence operates on a dynamically shifting physical topology. The network actually physically grows new bridges to connect discrete pieces of information.
Right. Now let's look at the digital replicas we've built.
Right, the transformer models. The architecture underlying every major LLM today. How does its structural routing compare to this agile axon?
It doesn't compare at all. It is the exact antithesis of agile.
Because it's static.
Exactly. Artificial neural networks use matrix algorithms to replicate processing. They take an input vector, multiply it across massive matrices of weighted parameters, run it through nonlinear activation functions, and spit out an output vector.
But the catastrophic limitation, the reason Lakeman calls them artificial, is that they don't search.
No. Artificial neurons do not search for new output connections.
The architecture is entirely baked in from the start.
Completely fixed. The topology of an LLM, how many layers it has, how many attention heads, exactly which artificial neuron feeds into which other artificial neuron, is entirely predefined by human programmers before the model ever sees a single piece of training data.
So the nodes are basically trapped.
They're trapped within a static mathematical manifold.
So when the tech industry throws around the phrase machine learning, it's actually a deeply constrained definition of learning.
Highly constrained.
Because if the topology is fixed, the machine isn't organically discovering new structural pathways between concepts. It's just tweaking the volume dials on the pathways we forced it into.
Exactly. In a modern LLM, learning is exclusively restricted to weight construction.
Just adjusting the dials.
Right. When the model is trained, it uses backpropagation to calculate the error of its output, and then goes backward through the fixed network, adjusting the mathematical strength of the connections that were already laid down by the architect.
It can turn a weight close to zero, effectively muting a connection.
or crank it up to prioritize it. But it absolutely cannot generate a novel structural connection between two nodes that were never mathematically linked in the matrix.
To go back to our analogies, the biological brain is like a river system.
Oh, I see where you're going.
When a massive influx of new water enters the system, the water actively erodes the landscape. It cuts new channels through the rock, it forms oxbow lakes, it physically alters the geometry of the earth to optimally route the flow.
The topology adapts to the data.
Exactly. But an LLM is like a city water grid made of cast iron pipes.
Right. The pipes are welded in place.
Yeah. When new data enters, the AI can only open and close the pressure valves, the weights, at the existing intersections. It cannot spontaneously lay a new pipe.
And if the optimal solution requires a pipe that doesn't exist, the system simply cannot reach that solution. It is structurally bounded.
Bounded. That really explains the hallucination problem in LLMs, doesn't it?
It perfectly explains it. Because they are trapped in a static matrix, they are forced to route queries through the existing parameter weights, even if the optimal conceptual connection doesn't structurally exist in the model.
So they just mathematically approximate a path through the fixed grid.
Right. Which often results in confidently outputting synthesized nonsense. They lack the biological mechanism of the agile axon, the ability to reach out of the matrix, hunt for the specific missing conceptual node, and build a bespoke, unweighted connection to it.
We've basically engineered an idiot savant and locked it in a mathematical straitjacket.
That's a brutal way to put it, but yeah.
It can perform matrix multiplication at a speed that defies human comprehension, but it possesses zero structural agency.
It cannot reach outside its pre-compiled boundary.
And because it's static, going back to our energy crisis, the only way we know how to make the system smarter is to manually build a vastly larger cast iron pipe system.
We add 1 trillion more parameters, which requires a nuclear reactor to power, and we still haven't solved the core issue of structural rigidity.
Which is why Lakeman's analysis doesn't just stop at a critique. He is actively looking for the escape velocity.
He is. If we know biological intelligence is based on agile axons seeking new connections, and digital matrices are structurally static, how do we fix it?
How do we artificially induce neuroplasticity into a digital framework?
And this introduces the final and, frankly, the most disruptive phase of our deep dive.
Lakeman's blueprint for the evolutionary leap to the superintelligence know-all.
He is proposing a specific mechanism to break the matrix.
So what is it? How does he mimic the agile axon?
He suggests we have to expand the LLM architecture outward. He proposes integrating aggressive internet search and find functions natively into the neural network's processing loop.
Okay, but we have to be incredibly precise here about what he means. Because right now we already have models that can search the web.
Right. Retrieval augmented generation. R.
Exactly. RG. If I ask a modern chatbot a question about today's news, it runs a separate script, scrapes a news article, dumps that text into its context window, and summarizes it for me. But Lakeman isn't just talking about a glorified RAG plugin, is he?
No, not at all. RAG is just an input trick. You are just feeding new text into the same fixed cast iron pipes.
So what is Lakeman proposing?
Something far deeper. He envisions a network equipped with what he calls analytic neurons.
Analytic neurons.
Yes. These are specialized nodes whose inherent function is not just to multiply weights, but to act as artificial axon terminals.
Oh, wow.
Their mathematical purpose is to actively search the external environment, the internet, and find responsive data structures.
So, under Lakeman's paradigm, the internet itself ceases to be a passive database.
Right. It becomes the structural extension of the neural network. The internet becomes an infinite landscape of acceptance, dendrites, and synapses.
That is wild.
When an analytic neuron queries the web, it isn't just pulling text to read. It is mathematically binding with the external data node. It forms a temporary dynamic structural connection.
It's dynamically altering its own topology in real time.
Yes.
The cast iron pipe suddenly sprouts a flexible hose, reaches out onto the web, connects to a server in Tokyo, pulls a specific data point, and integrates that data directly into its processing layer.
And the implications for how the machine learns are profound. We discussed how static LLMs learn through backpropagation, right? Adjusting weights to minimize error.
Yeah.
Lakeman argues that adding this auto search and connect capability injects raw, unprecedented processing power directly into the backpropagation loop.
How so? Walk us through the mechanics of that. How does searching the internet actually alter the math of backpropagation?
Well, in a traditional model, if the backpropagation algorithm determines the output was wrong, it only has one lever to pull, It goes back and adjusts the internal weights.
Yeah.
But if it still can't minimize the error because it just lacks the necessary data conceptually, it's stuck. It hits a local minimum.
It can't learn what it doesn't have.
Exactly.
Yeah.
But with analytic neurons acting as agile axons, if the backpropagation loop hits an error threshold, the network can trigger a search and connect function.
So it reaches out.
It reaches out, binds to a novel data structure on the internet, pulls it in, and fundamentally alters the landscape of the matrix.
It's no longer just optimizing fixed weights.
No, it is optimizing its own structural architecture to solve the error. It's mimicking the self-assembling neuroplasticity of a living nervous system.
And this structural agility is the prerequisite for the holy grail of cognitive science, which Lakeman refers to as some fairly dense terminology.
He does, yeah.
He states that this process of axon searching is exactly what expands intermodal intelligence metrics in the nervous system, allowing for the spread of modal inference.
It sounds complicated, but we need to translate that for the listener because this is the exact mechanism of genius.
Let's break it down. What is a modality?
A modality is simply a domain of perception or a specific category of knowledge.
Okay.
In biology, vision is a modality. Auditory processing is a modality. In data terms, quantum physics is a modality. Classical music theory is a modality.
So intermodal implies the connection of distinct domains.
Exactly. Modal inference is the cognitive ability to extract a structural pattern from one modality and successfully map it onto a completely different modality.
It's cross-pollination.
Yes. When a human observes the concentric ripples of water spreading in a pond, which is a visual and fluid dynamic modality, and then uses that visual pattern to conceptualize the invisible propagation of sound waves, they are engaging in modal inference.
They're making an associative leap.
Yes. And in the biological brain, those leaps aren't magic. They are physical. An agile axon literally grew a bridge connecting the visual cortex processing the water ripple to the frontal lobe processing the abstract physics.
Wow.
Lakeman's point is that a static LLM is horrific at true modal inference because it cannot build new bridges. It can only associate concepts if they frequently appeared near each other in its training data.
But if we grant the AI analytic neurons, if we give it the architectural agency to use the entire internet as a landscape of dendrites,
It can finally execute intermodal leaps on its own.
if it hits a processing roadblock in quantum mechanics, the analytic neuron can cast a net across the web, dynamically bind to a database of musical acoustics, recognize a structural resonance, and build a novel, unweighted connection between the two.
And that dynamic, boundless cross-pollination is what Lakeman concludes is the threshold event.
The leap to superintelligence.
Yes. It is the architectural shift that takes a limited, computationally bounded AI and enhances it into a superintelligence know-all. True machine intelligence, one capable of recursive self-improvement and genuine discovery, cannot exist as a static matrix on a server rack.
It needs the agile axon.
It requires artificial neurons that possess intelligent search and connect capabilities, mimicking the physical exploration of the biological brain.
But tracing this to its logical conclusion raises a glaring, almost existential contradiction.
Oh, definitely.
And if you are listening to this and mapping it against your own experience with the internet, you are probably screaming this at your device right now.
The internet is not a clean place.
It's a dumpster fire. If Lakeman's blueprint relies on the internet serving as the new landscape of dendrites, well, the internet is not a pristine, curated biological matrix.
No, it is a chaotic, unregulated abyss of noise, bias, hallucinations, and maliciously fabricated garbage.
Exactly. If we architect a system where analytic neurons are autonomously seeking out and structurally binding to web data, how does the artificial axon distinguish between a healthy dendrite and a toxic one?
You have identified the most critical vulnerability in this evolutionary leap.
Because it seems incredibly dangerous.
To understand the danger, we have to look back at how biology handles bad connections. In biological evolution, the growth of axons is heavily regulated by physical feedback loops tied to the survival of the organism.
Okay.
If an agile axon miswires itself, say, it connects a visual input of a predator to a dopamine reward center instead of a fear response, that organism gets eaten.
Right. Darwinian backpropagation, the ultimate hard reset.
Exactly. Biological neuroplasticity is kept mathematically honest by the unforgiving environment of the physical world.
But an artificial superintelligence operating via analytic neurons on the internet does not have a physical body.
Nor does it face physical mortality. If its analytic neurons reach out and build a high bandwidth structural connection to a massive repository of Conspiracy theories? Or pseudoscience? Or algorithmically generated noise?
It has no biological instinct to recognize the toxicity.
None. It would just structurally integrate the garbage into its core matrix.
The superintelligence know-all could recursively optimize itself into a state of highly efficient, mathematically bulletproof psychosis.
Yes.
It would be a genius that seamlessly infers connections between legitimate quantum physics and a subreddit dedicated to flat Earth theory, building its entire worldview on fundamentally corrupted dendrites.
Which means the grand engineering challenge shifts entirely. If Lakeman is right and the architecture of the future requires analytic neurons that can auto-search and bind, we are no longer just designing the matrix.
What are we designing?
We are burdened with designing the instincts of the artificial axon.
We have to program an artificial immune system for truth.
Exactly. We have to mathematically define the criteria by which an analytic neuron evaluates the logical integrity, the empirical weight, and the factual provenance of an external data node before it allows a structural connection to form.
And historically, as anyone working in AI alignment knows, mathematically defining truth or quality in an algorithm is incredibly elusive.
It is arguably the hardest problem in computer science.
Because truth in human language isn't a binary 1 or 0. We are right back to the original thermodynamic and structural limit.
We are.
Human context is a continuous, multiple-level analog spectrum, and we are trying to force a binary, discrete machine to autonomously navigate it. We are asking a system built on rigid ones and zeros to spontaneously develop the nuanced analog judgment of a biological organism.
We are indeed circling the core paradox here. Lakeman provides the structural roadmap. We absolutely need intelligent search and connect capabilities to break the static matrix, escape the energy crisis, and replicate the agile axon.
The blueprint for superintelligence is clear.
But executing that blueprint, unleashing a self-wiring dynamic topology across a landscape as polluted and chaotic as the global internet, is going to require breakthroughs, not just in hardware, but in our fundamental understanding of epistemological programming.
Let's pull the lens back and recap the immense conceptual ground we have covered today, because the implications of Lakeman's work fundamentally alter how we should view the trajectory of this entire industry.
It changes everything.
We began by stripping the semantic baggage off the word artificial. We established that while the digital neuron is a manufactured prosthetic, the execution of information synthesis is a real, measurable process.
We then exposed the catastrophic energy crisis inherent in our current paradigm. We analyzed how forcing a digital binary architecture to simulate continuous variables incurs the brutal thermodynamic tax of Landauer's limit.
Contracting the heavy, discrete state switching of GPU transistors with the elegant, low-energy, continuous gradients of biological analog bits.
We diagnosed the architectural dead end of modern LLMs, recognizing them as rigid, static matrices.
We compared their inability to autonomously forge new pathways with the physical dynamism of the biological brain, where agile axons literally slither and search to build unweighted connections and facilitate neuroplasticity.
And finally, we explored Lakeman's proposed evolutionary leap, equipping these models with internet-searching analytic neurons.
We discussed how giving the matrix the ability to structurally bind with the web mimics the biological axon, enabling intermodal intelligence metrics, modal inference, and the birth of a dynamic, self-assembling superintelligence.
It's a massive shift in perspective.
The reason this deep dive is critical for you, listening right now, is that it equips you with X-ray vision for the tech industry. Sometime in the next few weeks, a major AI lab is going to hold a keynote.
They definitely will.
They are going to flash massive numbers on a screen, trillions of parameters, massive context windows, exaflops of compute. They will likely heavily market a new agentic web search integration, promising that the model can now browse the internet for you.
But you are now equipped to peer straight through the marketing buzzwords.
Exactly. You understand the underlying biological architecture they are desperately attempting to emulate. When they announce a search function, you know it isn't just a consumer convenience.
You know it is a primitive attempt to build an agile axon.
You can evaluate their keynote not by asking, does the chatbot sound more human, but by asking the rigorous structural questions. Is this architecture still fundamentally trapped in a precompiled static matrix, or is it dynamically altering its own topology?
Are they just brute forcing binary data through a von Neumann bottleneck at the cost of a nuclear reactor, or have they fundamentally approached biological efficiency?
We began this discussion by examining how the label artificial obscures our understanding of the mechanics. It makes us think of a parlor trick rather than the real execution of a physical process. It lulls us into a false sense of superiority over the machines we are building. So I want to leave you with a final lingering thought to explore on your own, a thought that pushes Lakeman's thesis to its absolute limit.
What is it?
If Lakeman is empirically correct, if true machine superintelligence strictly requires an architecture that autonomously searches, actively grows, and dynamically rewires its own topological structure exactly like a living human brain, it dictates that the final form of AI will not be a neat, compiled piece of software sitting passively on a corporate server.
It will be static.
It will not be a fixed static map that engineers can audit, debug, or comprehensively understand. It will be an ever-shifting, natively unpredictable, living digital organism.
A living digital organism.
If an AI reaches a point where it is actively rewriting its own brain every single millisecond, sprouting new analytic neurons and severing old ones based on the endless, chaotic ocean of data it is binding with across the global internet, how will we ever be able to trace the superintelligence's thought process, let alone align it or control it once it develops the architectural agency to build conceptual roads we never designed, leading to destinations we cannot mathematically predict?